So as folks are continuing to make their way in, I'll answer a question that was asked by Sarah, which is what's the best way to grab an example of all the commands that we've learned to make a cheat sheet? So I think the two choices here are to rely on the RStudio cheat sheets, which are very nice, but are much more comprehensive and more for reference. Or you could go through the scripts from class and pull out the examples that we used in class and create your own cheat sheet from that. And I do highly recommend that exercise in general. I would say it's very helpful for me when I try to pull together a collection of ideas in an easy to reference form. Even if that's not going to be a canonical reference for anyone else, the exercise of building it and being able to reflect on it myself is very helpful, I find. So I think that is a cool thing to do. And you can go back through the scripts from day to day as a way of getting access to kind of all of that information to build that cheat sheet. Okay, so let's go ahead and get rolling with day 9. We're going to be talking about data visualization. So I'm hoping that this is going to be the most fun part of the course. And the kind of starting point here that you have probably observed already is that looking at data in tabular form is not really that helpful. So if I pull in the murders data set and look at the first few rows, that is something you want to do, but there are many, many fundamental questions that are very hard to probe looking at the data represented in this way. So as some concrete examples, how could you check, for example, which states have the largest populations, which have the smallest, how large is a typical state, what's the relationship between the population size variable and the total murders variable, and how do murder rates vary from region to region? So these are all very basic questions you would want to ask early on in your data analysis. And they're not so easy to answer in this tabular form. We can do it when we've answered many of these questions in some form or another by manipulating the data frame, but they all require some operation on our part. And for humans, it's going to be very difficult to extract this information quickly and easily in this representation. Whereas if you make a graph of it, then it's going to look like something like this. And well, okay, so there's some design work that goes into making this graph, and we'll spend a lot of time on this today. But you can see that there are lots of these very basic questions that are easy to answer. For example, what are the biggest states? California, Texas, and Florida. What are the smallest states? Wyoming and Vermont and DC. Is there a relationship between the two variables? Certainly the bigger population corresponds to more murders, but there is variance around that. And we even have this helpful dashed line here, which is showing the total number of murders that you would have if you had the national average murder rate. So states that are well below this line are having fewer murders on average than you would expect, and above the line, they're having more. Incidentally, I want to go ahead and run this cell. It doesn't mean anything for now, but it needs to be there for later on when we're going to use these packages, and I don't want you to have to wait at that point. So we'll just throw that cell execution in now. Okay, so the point here is well summarized by the adage that a picture is worth 1,000 words. Data visualization latches onto your visual cortex and the huge machinery that your brain has for processing information that is geometrically communicated. And in many cases, the visualization sort of is the analysis. So this is a recent XKCD that I felt was apropos that I am throwing in there, which is to say sometimes your data visualization is so clear about what's going on that you don't actually need to perform calculations to see that values are statistically significant and so on. You get the idea across just with the visualization. And this has been something that's been somewhat of a phenomenon in pop culture. So because the tools for doing these things have become increasingly good and the value of them has become increasingly recognized in industry and academia and government, as well as specifically news organizations. The website 538, for example, I think has done a great job of inducing demand for data journalism by producing quality data journalism that people then learn how to consume better and better as they read more of these things. And so infographics, if you're in this space, it's something that you've heard a lot of buzz about and you want to acquire skills for. So let's look at a few examples of this. So there's a Wall Street Journal article illustrating, or rather discussing and also illustrating measles cases in the US and the relationship with the vaccine. So you can see from the visualization here, this is kind of an example of what we were referring to a moment ago about patterns in the data, which are very clear from the data visualization without having to do subsequent modeling work or detailed statistical work to really take home the message quickly. So for example, measles cases in the 50 states year in and year out were consistently high. And then when the vaccine was introduced across all 50 states, they very swiftly petered out, right? So this is, I didn't intend it, but this is a real life version of the XKCD comic that we saw a moment ago. So here's another chart. This is coming from the New York Times, and this is about exams that students need to graduate high school. You would sort of expect that if these data were not tampered with in some way, you would have, a smoother histogram here. But instead, what's happening is you have very, very few students scoring just shy of what they need to graduate, and then a disproportionately high number of students scoring exactly the minimum threshold score to graduate. So clearly, this is very much pointing in the direction of some grade inflation around the minimum passing grade to make sure that students are able to graduate, right? And that's suggesting that the test is not accomplishing what you're intending for it. And this example illustrates how, if you are looking at helpful data visualizations, you can often find stories and recognize things that you need to investigate more carefully that wouldn't necessarily come out if you were just computing summary statistics or fitting models, that kind of stuff. So you want data visualization to be a core part of how you interact with data and think about interpreting a given data set. So there's a name for this. It's exploratory data analysis. And the idea is that you want to start your analysis not by bringing some battery of predefined methods and applying them to the data, but getting a feel for the data, visualizing it, slicing it different ways, looking at the values that are there to try to see if there are some aspects of the data set that you really need to have in mind as you move forward into more extensive analysis. So this is a quote from John Tukey about what we've discussed just now, seeing some patterns in the data that might not be clear in any other way besides data visualization. He said the greatest value of a picture is when it forces us to notice what we never expected to see. So one of the beautiful things about the sort of data-centric view of the world is that it can surprise you. You can have beliefs or ideas about the way the world is that get contradicted by the data, and that forces you to reevaluate and correct your beliefs. And data visualization can be a very important part of that. So here's one more example illustrating how data visualization can be used in philanthropic and educational contexts. So if you think about demographic trends in different countries and relationships between things like fertility rate and life expectancy, we have some narratives in mind about how those things vary by region across the world. And what this small data visualization is showing you is that those things can change a lot over time. Okay, so the momentum that common tropes tend to have, sort of stereotypes about the way the world is, it's not consistent in many cases with the way the world changes over time. So for example, in this visualization, we see that life expectancy is up across the board from 1962 to 2013. This whole picture is kind of shifted up. And there are many other things you can notice by looking at some of the details in this data visualization. I would say as well that this particular data set, the Gapminder data set, it's called, is common to illustrate interactive data visualizations, which we're not going to talk about. So we're going to focus on static data visualizations. But if you can have a slider that sort of takes you from 1962 to 2013 and see how these things move around, it looks really cool. And this data set is kind of a standard one to illustrate that feature. Yeah, so there's a question about this particular data visualization. What's the significance of color? So that's indicated in the legend. It tells you about the region. So we'll talk about this in some more detail, but basically the idea is that you want to use color, this visually discernible feature of the chart, to convey some meaning about the underlying data. And in this case, you're encoding this factor variable, the categorical variable, which says what region in the world a given country is in. You're communicating that with the color. So we'll see how to do that soon. So another advantage of using data visualizations extensively is that errors in data handling, things like mistakes or biases or other unexpected problems, can lead to a situation where your data is faulty. And models seldom account for these things. So you can often end up with incorrect conclusions because you're overly trusting your data. And data visualization can serve, at least to some extent, as a check on that. So this is just one other facet of using data visualizations as a core part of the way that you interact with data. Okay, so we're going to learn an approach to producing data visualizations that is reified in the package ggplot2 in R. Okay, so a little bit of introduction on ggplot2. So exploratory data visualization is one area where R really shines. So if we use ggplot2, we can go from idea to data to plot with flexibility and ease. And there are other packages which have some advantages and some disadvantages relative to ggplot. For example, Excel, which I think everyone has at least some experience with, it can be easier to generate some basic plots in Excel than it is in R. For example, you don't have to learn any coding. And if someone doesn't need coding for other reasons, then that might be very appealing. And of course, Excel has been very successful. But you're very restricted in how customized you can design the plot, or at least if you need to customize it very heavily, you're going to have a huge amount of work ahead of you. And for sure, there are some things you can do in ggplot2 pretty easily that are just actually not possible to do in Excel. And there's on the other end of the spectrum, there's a data visualization package called D3, which is in JavaScript. That's why it has the .js. And it is a lot more flexible and powerful than using something like ggplot2. You can make truly spectacular things in D3, very interactive and rich and interesting. But it's also a whole lot of work to make a single plot. And for exploratory data analysis, that's fatal. If it requires you to work a lot to make a plot, then you're going to make as few as you can get by with. And as we've seen, that can be really detrimental if you're not able to kind of slice the data lots of different ways, visualize it different ways, and start to get some intuition for the data set that way. So, these tools are certainly good, but they're sort of at extreme ends of the convenience versus flexibility spectrum. And ggplot2 is sitting at a very nice spot in the middle that trades those things off very well. I'll add, while we're talking about these sort of meta considerations, that when you talk about Python and Julia as an alternative to R, you'll have similar considerations. So it likewise sits kind of in the middle on the convenience versus flexibility spectrum. But they're not interchangeable. ggplot2 is pretty special. You don't have something quite as great as ggplot2 in either Python or Julia or anywhere else, as far as I know. By and large, when people talk about elegance of graphics package design, ggplot2 is held up as really kind of the shining example that everyone should look up to. There is some disagreement about that. Some people prefer a little bit more manual approach, like you'll see in Python or Julia. But by and large, this is a very admired piece of work. And it's one of the really special things about R. Okay, so let's go ahead and load the packages that we're going to use. We will use dplyr a little bit, and of course, we'll also use ggplot2. So we'll go ahead and pull that in. And the name ggplot2 comes from the phrase grammar of graphics. So the idea is that learning grammar can help a beginner who's just learning natural language construct hundreds of different sentences by just learning a small number of verbs, nouns, and adjectives. And the way that skill sort of sits in your mind is not through a massive memorization paradigm, but through a grammar, a set of rules for combining core objects to build more sophisticated objects. So likewise, we're going to learn a handful of ideas and concrete manifestations of those ideas from ggplot2. that are going to serve as the building blocks. And we'll also learn the grammar for how those things fit together. And then we'll have a lot of flexibility to create many different types of plots in a convenient way. And it's worth noting that ggplot2 gets a lot of its value out of a single design decision, which is consistent with the other packages in the tidyverse, which is that the data tables that you'll use with ggplot2 need to be in tidy format. So you can't throw sort of arbitrary looking data at ggplot2 and expect it to handle whatever comes at it. You might need to do a little bit on the front end to make sure that you can leverage the features of ggplot2 in a way that allows it to, sort of see what's in the data frame in an effective way. So this is not a universal design decision. You'll see many other graphics packages, including the one in base R, but also including plots.jl and matplotlib and many other libraries in other languages that don't have this design decision. You supply more or less raw data to the graphing system, and you have to therefore add labels yourself manually, and sort of all the information about how you want the graphic rendered has to be specified in a tailored way. Whereas ggplot2, because it's handling tidy data, it's going to be able to make a lot of decisions for you behind the scenes and give you some pretty good results really quickly. So this is debated, but in the vast majority of cases, it's totally fine either way because it's easy to convert the data into tidy format, or you already have it in tidy format. So this is at least a very reasonable position on the trade-off spectrum here. Okay, so I also want to mention, so that you can go ahead and pull it up if you want to, that there's this cheat sheet that we've mentioned before that is distributed by RStudio. And this is a helpful thing to have whenever you're programming in ggplot2, because you don't want to have to memorize all the commands. There are quite a few of them. They're principled, and so you will at some point through practice, you'll have a pretty solid grasp on lots of them without having to look at the cheat sheet. But it's really very low friction to look back and forth because you're typically going to know exactly where to look. And we'll see that in a minute illustrated. So I really just put that there so you can go ahead and load it up. Here's a visualization that we saw earlier for the gun murders data frame. And this sort of looks like something that was maybe pulled from an online publication. In my opinion, it looks very professional. There are all sorts of things here that you would think require a lot of manual work. Like, look at this, these labels, and you've got an arrow here from Virginia because somehow, there's not space to fit it in right next to the dot. There are lots of things here that you would think, this must have taken someone a ton of time, someone very professional, and our plots are not going to look this good, of course. But actually, this is generated by a very modest amount of code that we're going to work up to today. And we'll see how to do all of these things, and we'll see that it's very concise and elegant. Okay, so a couple of points about what we're looking at here that we've already made these observations, but just to reiterate. So we can see the relationship between population size and total number of murders. As you move to the right, you also move up, generally speaking. And we also have this dashed line indicating how many murders each state would have if its rate were consistent with the country at large. As we also mentioned earlier, the geographic regions are indicated by color. So you can quickly glance and tell where, for example, the green states here, which are in the South, where they're consistently sitting above this line. So we saw earlier that they have an above average murder rate compared to other states. Whereas in the West, by and large, the states are lower. So you have California up here just above the line, then all these other states are below the line. So these are things that you can quickly ascertain from looking at this visualization. And one thing that's cool about this particular visualization is that it's not hiding very much. Pretty much everything that's in the data table is there in some form in the graphic. And we're going to learn how to do this piece by piece. First step in learning how to use this package is going to be to look at the graph and think about what's there in structured terms. And then we'll be able to map that structured understanding of how the data visualization is built into code that will produce the data visualization. So I'm going to share this comment. So one of the keys to using ggplot2 effectively is understanding how the elements of tidy data translate to the elements of the visualization package. Exactly, that's perfectly put. Okay, so let's introduce some grammar of graphics vocabulary here for thinking about this plot. You know what? I think I'm going to go ahead and pin this if we have space so that we can keep seeing it. It is quite big. It might be nice if there's like a resize on the pin here. So we could change the size of this thing. Anyway, okay, so the main three components to note are the data, of course. So that's not really, you don't see the data table in this visualization directly, but that's obviously an important part of it. In order to place everything where they go and make the right colors and all that stuff, we have to have access to the data. And in particular, the plotting system needs to know what data it's looking at. So this is the data component of the visualization. And the second component is called a geometry, or geom. And what we have here is a scatter plot. So the data is being visualized specifically through points. You know, you've seen line plots and bar plots. There are lots of geometric objects that one can use to represent data. And here we're using points. So we have a scatter plot. And we'll learn more about these as we move forward. And the third thing is called the aesthetic mapping. So this is the correspondence between the first two things. The geometry is telling us we want to use points. The data is telling us something about where those points should go. But the aesthetic mapping is what's required to sort of bind those things together. Okay, you can't just say, here's my data, I want a scatter plot. Go after it. You need to say which columns you're looking at to associate with the horizontal and vertical axis, and what column to look at to determine the color and all of that kind of stuff. So that's called the aesthetic mapping. So let's just practice listing some of these. I named a couple just now, but I'll give you a chance to either repeat some of those or notice other ones if you want. So the question here is, what are some visual cues in this visualization? So what are some visually discernible features of the plot which are being mapped in some correspondence to the underlying data? So the first one folks are noticing here is that the color is being associated with region, as we said. So that's exactly right. So that there is information from the data table, which is visually discernible here, through the color choice being made for each point. What are some other ones? Yeah, here are a couple other ones that you don't think of as visually discernible features in the same way as color, but it's also important. So logged population is being mapped to the x-axis. That's right. So the horizontal position in the graph is a visually discernible feature. If I took this Kansas dot and moved it way over here, that would correspond to, you know, Kansas growing in population by a bunch, and it would look different in the graph. So horizontal position, it's actually much more powerful than color because of the way that your eyes process information. You can detect small differences in horizontal position, whereas differences in color, you need more contrast to really tell what's going on. So certainly one of the most important aesthetic mappings is to say which column in the data frame, which attribute or feature you're going to be associating with the horizontal axis. So horizontal position is an important example of an aesthetic to map to. Same thing for vertical position. And then, yeah, we have the regions and the colors here. Yeah, so let's talk about a couple of things that aren't really aesthetic mapping so that we can see the contrast here. There was one other one. Oh, yeah. So here are a couple things that you can see in the graph. So there's the regression line, this dotted line here. And this is something that we're sort of adding to the plot kind of after the fact. This is not going to be pulling something directly out of the data frame. So you want, in order for it to be an aesthetic mapping, it's something that should vary row by row as the values in the table vary. Whereas this dotted line is really, it's, I'm not sure I have good vocabulary for it, but it's not something that we're going to have to tell the plotting system, here's what column to look at to make this plot. Rather, we're going to have to pull out the appropriate slope for this line using some ad hoc calculation, and then manually sort of say, hey, draw this extra line in on top. All right, whereas what we're going to be able to do with all these other things is say, okay, give me colors based on this column, and we don't have to manually do all of that. And likewise, the choice to use log scale here, it is part of the way the aesthetic mapping takes place. If you want to say where a dot goes, you need to know that it's a log scale rather than a regular linear scale. But it's not something that you have to specify directly in that way. So we can separately say, okay, horizontal axis goes along with population size. And then also we can say, by the way, the x-axis should be log scaled. So this is going to, so scales are not going to sort of fit into the aesthetic mapping framework. They're sort of like this dotted line. They're kind of extra options that we're going to specify on top. Yeah, here's another great example of the same thing. So these are style choices, like the fact to use the idea that you want to use a white line here or have this sort of slate gray background, whatever color that is. These are style choices that are not connected with the data. So those are global style choices that do not require specifying a particular data correspondence. Right, so these things will become more clear as we move forward, but I wanted to have a little bit of abstract talk about them before we get the code going so that you can be prepared for what you're looking at. Okay, so yeah, so just kind of summarizing that, I might have to unpin this so we can actually see. I don't think I've done this before with quite so large an image. So this is, well, it's a good thing for me to see about what happens when you try to pin a really large image. Okay, so each point in the visualization represents a different row of the data frame or a different observation. And what we're doing is we're mapping data to visual cues like like the horizontal and vertical position or color and so on. So map is kind of the key word here. So this is called an aesthetic mapping. So there's a question, would we always want to use the log scale for large populations? I would say, pretty much whenever your data spans several orders of magnitude. So in other words, the largest observation for that particular feature is many times larger than the smallest. Yeah, it's likely in that case you should consider a log scale. And the reason is that the values near the top of the scale are going to dominate if you use a linear scale, and you can't really see the detail down at the bottom end of the scale. It's really about the fact that if you take the log, you get a more consistent distribution for this particular data set. There's sort of, it's more homogeneously spread out within the range, and that is good for visualization. There was one other question, very astute. The labels also require an aesthetic mapping. Yes, so I forgot about that one. So you do need to look at the abbreviations column in the data set. Like this NH that's printing here is printing that way because that particular row has an NH in it. So this is not manually added. We're going to say, hey, ggplot2, I want to put labels on things. Look at this column to produce the labels. And when we do that, we're mapping. We're associating a particular column in the data frame with something that's going to be visible in the final plot. So yeah, that's a great point. All right, so the way that we're going to define these aesthetic mappings is going to depend on, I might have to get rid of this now. The way that we define these aesthetic mappings is going to depend on what geometry we're using. So different geometries may have different needs, and so they're all going to be designed a little bit differently. Yeah, okay, so just a few points. We've already hit some of these. Actually, I got a little bit ahead, but just to put it down. So the points are labeled with state abbreviations. That's another aesthetic mapping we'll have to come up with. The range of the x-axis and the y-axis are defined by the range of the data. So we have it set so that there's no extra space on the left or right. That would be what you would often want to do, because otherwise you're just kind of wasting space. Also, they're both on log scale. So that means that the axis is warped by the log function so that each distance unit in the graph corresponds to multiplication by a factor rather than addition of some value. And there's also various style elements here, labels, a title, legend, and the overall style, the color of the background, and some of those other things we mentioned are coming from The Economist magazine. So obviously that's not something you would know just by looking at it, but that's some information that I'm giving you now. Okay, so what we're going to do is just build this up slowly over time. So we'll start with something actually something empty, and then we'll have something very crude, and we'll just refine it over time. But to start, we do need to go ahead and load our data. And the very first thing that we're going to do is create what's called a ggplot object. And by itself, this object doesn't really do anything. It just stores information about how we want the visualization to be built. And then when it's rendered to the screen, that information is translated into an actual graph. And because we're working in Jupyter cells, we can just run this code and the output will display immediately. So we start with our ggplot command, and we tell it we want the murders data set to be the one we're building on here. And alternatively, we could pipe that in because data is the first argument in the ggplot function. So we can pipe that. This is equivalent. And there's nothing here. So we just get this plain gray background. And that's because we haven't told it anything about what we want to see. We've just said, here's the data we want to use. But we need to say what geometry should be used to render that data. And we'll also have to produce an aesthetic mapping. So because we didn't assign the object to a variable here when we created it, it just rendered to the screen, but we could save it as a variable so that we can update it later and try adding different things to it and so on. So let's just see what this looks like. So suppose we store our ggplot object, which has the murders data set associated with it, as the R variable P, and then we ask what the class is. It's going to tell us that it's a GG object, which is a special case of a ggplot object. Okay, so whatever that means, the important thing is this is a special kind of object that's being used to store our information. If we want to see a particular ggplot object that's storing some data, we can either just put it on the last line of a cell, in which case it's automatically displayed to the output area. Or if we want to do that from somewhere inside some other code, we can call the print function on it. So this first one rendered this first blank screen, and the second one rendered the second one here. Okay, so a plain ggplot object, as we've seen, is completely useless. We need to start adding stuff to it to make it useful. And the things that we add to it are called layers. So layers can do several different things. They can define geometries. They can compute some statistics of the data in order to render the data in some more interesting way. Or they can say what scales we want to use, change styles, and various other things that we'll learn as we continue to move forward. So layer is a generic term encompassing several different kinds of extra information we can add to our plot. The way that we add layers is with the plus symbol. So we'll start with our data, we'll pipe it into ggplot to create a ggplot object with that data associated with it. And then we'll add layers one at a time, just continuing to put the plus sign in the next layer and so on until we've got all the layers we want. Okay, so typically the way this is going to be designed is that the first layer adds the geometry, okay, and then further changes that we might want to make will be in subsequent layers. So we first want to say which geom are we using, and in this case we're trying to create this visualization that we started with of the murders data set, and so we want a scatter plot. So which geometry corresponds to the scatter plot? So take a look at the cheat sheet that I linked to earlier if you have it pulled up. If not, then you can just hang tight. Someone else will do it for you. But just give you a little practice at looking at that and starting to see kind of what's there, how it's laid out. Okay, so I'm glad that I did this and gave folks some time to respond, because I'm seeing a variety of answers. And I sort of thought there would just be a unique answer, but this illustrates an important point. So geom_point is what we're going for here. I'm going to go ahead and send this message so we can look at the cheat sheet together. Here we go. So geom point is right here. So this is the one that we want. But there are other things with dots. There's geom jitter, which lots of people noticed. There's geom dot plot, which also has dots. This one we can tell it's probably not the right one because it's for only one variable, whereas a scatter plot is for when you have two variables. So you'll have an X and a Y. That's what we have here. So it should be in this area. But still, that leaves us to geom jitter and geom point. And what's the difference between those things? Well, this is partly an artifact of cheat sheets being highly condensed. It's not going to explain that here. It's trying to explain it a little bit by having these points kind of snapped to the corners of the grid and having these points kind of shuffled around. The jitter geom is going to put points down, but it's going to move each one a little bit left, right, up, or down, sort of in a random direction near the original point. And that way, if you happen to have some points stacked on top of each other, you can kind of see a little pile of points there instead of just really kind of seeing just the one. But we don't need that here because we're not going to have coincident points. So we're just going to want to use geom underscore point. All right. So there's no way you could tell the difference between this two. You'd have to look it up. Then, of course, once you learn it, the name is quite suggestive, jitter. You'll probably remember it pretty well. And as you can see, looking at the cheat sheet, all of these things follow some basic pattern. It's geom underscore and then the name of the basic geometric object, either a point or a bar. You can also have Geom Histogram, which is a bar plot, but it goes ahead and performs the appropriate statistical transformation to take your one variable of data and make it a 2D plot. So you'll have X and Y values here. That requires binning the data and the histogram function. It's really kind of a convenience function to do that for you. So really the kind of core geoms are geom point and geom bar and other things like that, which are shown here. Okay, so for geom point to work properly, we need to not only say we want points by specifying geom underscore point, we also need to say what variables the X and Y values correspond to, or the horizontal position and vertical position correspond to. So what we can do is read the aesthetic section of geom point, and I'll just put that relevant section here. It takes X and Y in the first two positions, as you'd expect. It also takes an alpha argument, and alpha is a synonym for opacity. So it's going to be transparent if you use a lower alpha value. By default, alpha will be 1, which means fully opaque. That's what we'll stick with. But if you did want to make it something you could see through a little bit, you would lower the alpha value in some way. And color also, which again, we have here a British spelling, but you can also use the American spelling. Both are supported. Okay, so we can see X and Y are there, which you would expect. If you want to make a scatter plot, you need to say which variable you want to plot along the horizontal axis and which variable you want to plot along the vertical axis. And those indeed are the first two arguments there. Okay, so we can't, however, just say, so you might expect that what we should do is just add a new layer, which is defined by geom point, and just say X equals whatever the X variable we want is, Y equals the name of the Y variable we want. That doesn't work because the way ggplot is designed, if you are mapping variables from the data frame to aesthetic elements in the visualization, you need to use the AES function. So this is short for aesthetic mapping. And the idea is that you're explicitly communicating that information should come from the data frame. So we'll have to wrap the X equals and Y equals parts of what we're doing here with the AES function. So maybe that's all a bit unclear without some concrete code. So here's a piece of running code. So we start with the murders data frame. We pump it into the we pipe it into the ggplot function. And then we add another layer to that resulting object. So this happens first. It produces a blank slate that knows what data to look at. And then we say, okay, we're going to create an aesthetic mapping, which says that the horizontal position is going to be associated with population and the vertical position is going to be associated with the total number of murders. And then this produces an object, which it's sort of like just saying X equals and Y equals directly in the geom point call, except it's supplying further information to the geom point function, which is letting it know that it is getting these data from the data frame that the ggplot object is holding. So this is our first non-trivial ggplot example. We just started with a basic ggplot object and then added a geom point layer to it, which has an aesthetic mapping associating the population with the horizontal axis and the total number of murders with the vertical axis. So when we do this, just like with any R function, we could drop the x equals and y equals if we wanted, because those are the first and second arguments in geom point. So we also could have, instead of doing all of this calculation in one fell swoop, we could have added to the object P that we defined earlier, the geom point layer. So that works just as well. So these are ordinary R objects. You can use all of your standard R knowledge to change how you manipulate them. So here we're just using this short name P that we assigned earlier to the kind of blank slate ggplot object, which only contains the data. And one thing that you can notice when we did this is that we get a lot of stuff for free. So we get labels. We have population over 10 to the 6th as our label on the x-axis. We have total as our label on the y-axis. We got that just by virtue of the data coming from a data frame. So ggplot2 knows where to look for that stuff. And the scale here, we're using a linear scale on both axes. And that also was chosen by default. So it's not like you have to make every single decision in order to get a plot up on the screen. Everything has sensible defaults that you can then override if you want to. So as we've been discussing, dplyr functions and the AES function have in common that you can refer to a variable in the data frame without having to reference it with the $sign. So you just refer to it directly and it knows I should be getting that from the kind of ambient data frame that lives in this ggplot object. However, unlike dplyr functions, this is neatly separated out. So if you put your reference to population or total outside of the AES call, then you'll receive an error because the geom point function is specifically designed not to do that. So if you have something that's outside of the AES call, then you will need to be referring to actual variables in your R session. So I had a question from a minute ago, which inserts perfectly right now. So I'll do it. And this is exactly right. So if you have an object defined outside of the data frame and you call that outside the AES function, it will use that object from your session. That's how this works. Okay, so we have a good start now. Let's add some more stuff. And there are various ways you could go about kind of touching up the graph we have now to make it better and better and look more like the kind of final version that we're aiming at. But what I want to do next is add text to the plot. Okay, so we have our scatter plot, which was added here. And then also in the cheat sheet, you're going to see a geom_text, which allows you to add text to the screen. And likewise, as we mentioned earlier, there is a mapping here between the variable from the data frame, namely population, and the text that should appear. So we'll need to tell this geom text object that the X value should come from population, the Y value should come from total. That's the same as this because we want to put the labels where the points are. But then we also give it another variable, namely the abbreviation column associated with the label argument of the geom text function. And that makes sense. For a point, you just need to know X and Y. And for text, you need to know X and Y and what to write there in order for it to make sense. So this is how that's going to look. And well, that's something. I think it's pretty ugly, but it's a starting point. We see that, California is up here, Texas, Florida, New York. So yeah, it seemed like this worked. All right, so we successfully added a second layer to the plot, but it's going to take some effort to make this nicer. So just to illustrate this point we were discussing just now about the aesthetic function, if you put the label argument outside of the aesthetic function call, then you're going to get an error because it's going to try to grab this from your R session, which doesn't exist. This variable ABB only exists as a column of your data frame, not as a function in your session. So when you try to run this, you will get an error that says ABB not found. Okay, so the point is you can put it outside if it does not associate with any particular data in the data frame. but you need to put it inside if it does. That's really it. Okay, so each of these functions will have some arguments other than the aesthetic argument and the data argument. So they're going to be specific to the function in most cases. So for example, in the plot that we want to make in the kind of original version we're looking at, the points are larger than they are in the plot that we have so far. We're going to need to increase the point size. And there's a size argument which will allow us to do that. So when we call geom point, we say size equals 3, and we put that outside of the aesthetic function call because it's applying to all the points equally. There's no mapping between the data and the aesthetic that we're changing here. All right, so that right now it looks worse because the labels are right on top of the points, and now the points are kind of swallowing up the labels. We'll fix that. But we did make the points bigger, so that we're making progress. Here, this message just reiterating what I just said. This goes outside the aesthetic function call because it is not associating anything with data from the data frame. It's just an option. Okay, and to address this other point that we just ran into with this ugliness in the plot, we'd like to move the points. Sorry, we'd like to move the labels slightly off so that they're not sitting right on top of each point. And you can look at the geom text help, and you can find that nudge underscore x is the argument that allows you to do this. So if we do nudge underscore x, and you'd want to experiment with this value if it didn't look just right initially, but 1.5 works well here. And it moves the labels over to the side. So it looks way better now, especially out here where there's enough space to really see things. You can really tell what's going on from one state to another. Okay, so next time we're going to learn a better way of keeping the labels from kind of colliding with each other. But this is at least a start. So one thing that we can put in now to kind of clean up our code, and this is useful quite broadly when we're dealing with ggplot, is that we can simplify this aesthetic mapping a little bit, because for both the points and the labels we want to use the same x and y, and we had to repeat that. And you can imagine you might want to put something additional on the graph which also would associate x and y with these particular variables. So you might want to use what's called a global aesthetic mapping, or in other words, you tell your ggplot object up front, hey, in this visualization, unless otherwise specified, x is going to be population over 10 to the 6th, and total is going to be corresponding to the vertical axis. And that way you can call multiple geometries, add multiple layers without having to specify that aesthetic over and over again. And you can see that this is the second argument to ggplot, the ggplot function. So we can just put that in there. All right, so this is what it looks like. We start with our murders data frame. We pipe that into ggplot. So that's now going to be the first argument in this function call. So ggplot of data, namely murders. And then the second argument is going to be whatever's put here. And we could say mapping equals, but we can also drop it, since it will automatically be the second argument by virtue of murders coming in here as the first argument. And what's that argument? Well, it's an aesthetic object, an object returned by the aesthetic function, which says x is population over 10 to the 6th, y is total. And if there's a label attribute, then if your geometry has a label attribute, then it should be associated with the abbreviation column. And then we can simplify our code a lot after we get p defined in this way. We can add geom point to it and just specify size now. We don't need to specify the aesthetic to the point geometry because it's already stored there in p, and that we'll grab it from there. Likewise, we don't need to store any of the other variables here, x, y, or label, to the geom text argument, or sorry, to the geom text layer, because again, it will get those from the p object where they're stored. So we just need to supply the ones that are specific to this particular layer that we're adding. All right, so we get the same thing, and our code is looking quite a bit cleaner now. All right, so that brings us to time, and we're kind of in the middle of things here, but that's fine. We'll just pick up from here and move forward with the rest of the data visualization material. And at the end of it, we'll indeed have, with just a handful of additional operations like the ones we've learned so far, we'll have this very nice visualization that we started with at the beginning of class that we're targeting now. So it's great seeing everybody today. And yeah, we'll see you next Tuesday.